So rates of change, and as we've seen, our derivative, that's what measures our rate of change, as one quantity changes with respect to some other quantity. And we know this also, that the steeper the curve, then the faster that quantity is changing. So if I've got a graph like this, there we go. Over here at the point P, I know that, well, the derivative is positive there because that line's got a positive slope. So yes, we say, well, yeah, that's increasing. And even just looking at the picture, we can see that it's going up. And Q sitting at the top there, that'd be when, well, there is no change at this stage. The tangent is horizontal, the derivative is equal to 0. That's what we call our stationary point, so the curve is stationary there. And then of course we've got the other situation where we're going down. That's where the tangent has a negative slope, so the derivative is negative, and we say it's decreasing. Okay. Now, if I've got 2 points on that curve, if I was to draw a line between those 2 points, the slope of that secant, a secant being a line that cuts a curve in 2 or more places, that would give us the average rate of change between P and Q. We tend to be more interested in this one. Here's a single point, and if I draw the tangent into that point, the slope of that tangent there gives the instantaneous rate of change. So what's happening at that exact moment? I'm now going to bring us back to an idea that, gosh, when's the first time you saw travel graphs? Year 8, year 7, maybe even in primary school. Here we go. Typical sort of one we saw. We had nice little blocky lines and things like that. Is a coach leaves the depot at 9 a.m. for a one-day tour, and there's our graph. Now, you probably didn't realise it at the time, but you were actually doing some calculus with this. Because the sort of things we asked were, how long's the first stop? And how did we work out where the first stop was? Well, we were looking when that line was horizontal. And let's tie that back into calculus now. Horizontal tangent, that's when the curve is stationary, that's where it stops. Oh, how long was it? Well, it's stationary for 30 minutes. When did the coach start to return to the depot? Oh, in calculus, we'd be saying, well, when is this function decreasing? When are we coming back? So when's the distance we're away getting smaller? And so on our travel graph, we were looking, well, when's the line going back down? Oh, it was at 1:30 that happened. How fast was the coach travelling on the return trip? How fast was it travelling? Well, we would have worked out speed equals distance over time, and the return trip, it's travelled 200 kilometres over 2. Well, what we've actually just worked out is the slope of that line. Well, the slope measures the rate of change, and that's what speed or velocity is. It's the rate of change of the distance or displacement, depending on whether we're talking about speed or velocity. Calculate the average speed for the whole trip. Oh, again, speed equals distance over time. We travelled 400 kilometres all up, divided by 61.5 kilometres per hour. Those are the sorts of things we saw way back when. But now we don't have to have little blocks anymore because we've got calculus, we've got other functions we know. We actually can work out for this sort of graph that the equation is x equals 5t times 8 minus t. It's a quadratic, our picture's a parabola. Remember, distance is the total amount travelled. That hasn't changed just because all of a sudden it's a curve instead of a straight line. Displacement is how far away are you from, well, usually the starting point, but they might say, well, from another point as well. Find the height of the ball after 1 second. Well, now I don't actually need the graph, because if I've got the formula, I can substitute it. So t equals 1, x would be 35. So I know, all right, after 1 second, the ball is 35 metres above the ground. Now, when you're answering these sorts of questions, that's exactly what you should do. I personally wouldn't leave it as x equals 35. That's just the maths I use to find the answer. If they're asking me a question, I answer the question. So after 1 second, the ball is 35 metres above the ground. At what other time is the ball the same height? Sure, if you've got your graph, you could rule a line and draw off. But again, we've got the equation, so we can say, well, we're trying to find when x is 35. Solve this quadratic. We already know one answer, of course, which was t equals 1. The other answer is t equals 7. Again, interpret the answer. Then I know, well, it's going to happen again after 7 seconds. Average velocity, that's the change in displacement. So displacement goes with velocity over change in time. Very similar to the slope formula, I guess, because again, remember we're saying it's the slope of the tangent, or in this case the secant. So find the average velocity during the first second. It will be 35 minus 0 over 1 minus 0, 35. So where it was at t equals 1 minus where it was at t equals 0. That's my average velocity, 35 metres per second. Find the average velocity during the fifth second. So the fifth second would be starting at t equals 4, ending at t equals 5. So let's find those points. When t equals 4, we get 80. T equals 5, we get 75. But this is the difference with speed and velocity. With velocity, I can get negative numbers. So negative 5, so there's its velocity, negative 5 metres per second. Now that negative number has meaning. Basically it's talking about the direction it's travelling. So positive, we're going in, well in our case we're saying up was positive, so we're going up. Negative means, oh, we must be travelling down. Find the average velocity. Well, the average velocity is 0, which sounds kind of weird because this thing has moved up and moved down. How could it average nothing, like it hasn't moved? Because we're talking about velocity, not speed. We started at the ground, we ended at the ground. So on average, my velocity is 0, because had I not done anything, I would have been in exactly the same situation. So averaging out, the velocity is 0. Average speed, as opposed to average velocity then, is distance over time, that formula we're so familiar with. So when we're working out speed, we use distance. When we're working out velocity, we use displacement. Now if I find the average speed during the 8 seconds, now we'll come up with a number. Distance over time, well, it's 20. So we're averaging 20 metres per second during that whole journey. So 9A, just a quick little start there on motion. We're going to look at motion.